Alrighty, in this video we are going to be talking about alternating series error or Lagrange error, because sometimes on the AP exam they won't tell you which one to use, so you'll need to figure out whether it is alternating series error or Lagrange. So looking at 14a, we want to consider the fifth degree Maclaurin polynomial for sine of x, and we're going to use that polynomial to approximate sine of pi over 15. So remember that the fifth degree polynomial of sine is going to be x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. We're going to be using that Maclaurin polynomial to approximate sine of pi over 15. So anytime I see an x, I'm going to replace it to a pi over 15 and call it a day. Oops, that should be a 5. All right, for part B, it's asking us what's the maximum error possible using this approximation when x is between negative 0.3 and 0.3. So we're talking about this approximation right here from part A, our fifth degree Maclaurin polynomial. And what happens whenever x is between negative 0.3 and 0.3. So notice how for sine, we know that it is an alternating series. And if our series here is between negative 0.3 and 0.3, you'll notice that the terms will decrease in terms of absolute value to 0. So we could use alternating series error, meaning that I'm just going to look at my next neglected term. In this case, my next neglected term is going to be x to the 7 over 7 factorial. So my maximum error should be in the form of x to the 7 over 7 factorial. But since x is between negative 0.3 and 0.3, we know that x right here, we could say that x is 0.3, and then that's going to give us our error. All right, and then for part C, it's asking us for what values of x is this approximation from part A. So this approximation right here is accurate to within 0.00005. So once again, we know that using the alternating series error, our neglected term is going to be x to the 7 over 7 factorial. That has to be accurate to within 0.00005. And essentially we're solving for x. So we have x to the 7 is less than or equal to 0.00005 times 7 factorial. And then if I take the 7th root of this, I get this lovely thing right here. And essentially this is saying that whatever x value is, this is our approximation, our fifth degree Maclaurin polynomial is going to be within 0.00005 here. All right. For 15, we want to look at the maximum error when a second degree Maclaurin polynomial is used to approximate ln of 1 plus x for absolute value of x is less than or equal to 0.2. So x is within 0.2, whether it's positive or negative. I'm going to show you two methods, and then we'll see that there's one better method, so aka Lagrange and alternating series error works here, except I prefer alternating series error because that's a little bit easier, but I will also show you the Lagrange way. So using the Lagrange way, we know that error has to be less than or equal to the third derivative, since we are looking at a second degree Maclaurin polynomial. So we want to find the third derivative at z. We've got to figure out what that is. And then we have x minus c. Our center is at 0, so we just have 0.2 to the third power over 3 factorial. Now to figure out that third derivative from 0 to 0.2, we got to figure out that. So we have our first derivative being 1 over 1 plus x. We have our second derivative being negative 1 plus x to the negative 2. And then we have our third derivative being 1 plus x to the negative 3. Or 2 over 1 plus x to the third power. Now, to figure out the maximum derivative between 0 and a 0.2, what we're going to do here is just try and plug in and see which one is the maximum. So we have 2 over 1 to the third, or we have 2 over 1.2 to the third. Since we have a higher denominator here, this is going to be a smaller value, which means that this right here is going to represent my maximum derivative at 2. So this is going to tell me that my error is going to be 2 times 0.2 to the third over 3 factorial, so whatever that is. Now, you'll realize that what's going to happen here is that this is going to be the same thing as my alternating series error that we'll do in like 2 seconds. Now, hopefully you saw a pattern here in terms of my derivatives, or if you memorize the Maclaurin polynomial for ln of x, we knew that the Maclaurin polynomial for ln of x is in the form of -1 n minus 1 x minus 1 to the n over n. So if I were to build that and do 1 plus x, I'll get -1 n minus 1 x to the n over n. Now, since we have a second degree Maclaurin polynomial, our next neglected term is going to be my third term. So if I were to find my third term, I'm going to have -1, 3 minus 1, x to the 3 over 3. And since x is within 0.2, I'm going to go ahead and plug in 0.2 here. So error is less than or equal to this lovely thing right here. And you'll see that this becomes 1, and this becomes 0.2 to the third over 3, which is the same thing as this, because if I were to simplify this right here, I'll get 2 over 6, which is 0.2 to the third over 3, aka the same thing as this lovely thing right here. So using Lagrange or alternating series error, either way works, but just thinking about the AP exam and thinking about which one's more efficient, I would probably use alternating series error. Now, of course, you still have to justify why you're using alternating series. So you just got to say that, hey, this is an alternating series. Use terms decrease in absolute value to 0, and then verify that. Okay. I'm going to skip 16, and I'm going to focus on 17, where we have ln of 1 plus x cubed, and they have already given you the Maclaurin series for that. Now, we want g of x, and that is the integral from 0 to x of f prime of t squared dt. And we're going to find the first 3 non-zero terms and the general term of the Maclaurin series for g. Okay, so what we are going to do is build this by taking the derivative first, since this is the derivative. Now this is f prime of t, so if I were to build this, I'm going to get 3t squared minus 3t to the 5th plus 3t to the 8th. And then that's going to give me -1 to the n, 3n plus 3, and then t to the 3n plus 2 all over n plus 1. Now I'm going to simplify this a little bit because she looks pretty nasty right now, but you'll see that with the 3n plus 3 and the n plus 1, that can be simplified down to 3. So I can have this right here. Okay. Now, what's going to happen is we have t squared inside my argument. So now building my t squared, I'm going to have 3t to the 4th minus 3t to the 10th plus 3t to the 16. And then building that, I get, let's see, that's going to be 6n to the 4. Now what we're going to do is go ahead and integrate this from 0 to x of f prime of t squared dt. So if I were to do that, I'm going to get, let's see, 3t to the 5th over 5 minus 3t to the 11 over 11 plus 3t 17 over 17. And then that's going to be negative 1 to the n, 3t 6n plus 5 over 6n plus 5. Pretty nasty, I know. Now, remember that this is still bounded from 0 to x, so we are just going to use F2C and plug in x. 0 doesn't really matter just because this is centered at 0. So my final answer is going to be 3x to the 5th over 5, 3x to the 11 over 11, plus 3x to the 17 over 17. And that gives me my first 3 non-zero terms. And then the general term is going to be negative 1 to the n, 3x to the 6n plus 5 over 6n plus 5, since that's not x. Okay. Now, part B says, use the result from part A to approximate the integral from 0 to 1 through x to the 4th over 1 plus x to the 6th with error less than 0.2. Now, as you guys can see, we have an alternating series error because my terms are alternating, and it's going to decrease to 0. Now, essentially, since we're going from 0 to 1, our terms are going to be 3/5, 3/11, 3/17, 3 over 23, 3 over 29, and so forth. Now, we just need to figure out which one has an error that's less than 0.2. So if I were to look at this, if I were to use my next neglected term, that's going to be this term right here at 3 over 17, because 3 over 11 is going to be, what is that, like 0.27, so this is like 0.27 here, and then 3 over 17 is going to be 0.17, which is going to be error less than 0.2. So to approximate the integral from 0 to 1 of 3x to the 4th over 1 plus x to the 6th, since this is my next neglected term, I'm only using my first 2 terms here as my approximation of this integral right here. So the integral from 0 to 1 of 3x to the 4th over 1 plus x to the 6th is this little big thing, because this right here gives an error that is less than 0.2. Okay. For number 18, we have this lovely thing right here from 2023 BC6. And we want to find the 4th derivative of f with respect to x. And then we want to write the Taylor polynomial for f about x is equal to 0. And then we want to show the work that leads to our answer. Okay. Now, we are given we're given the 3rd derivative, which is this thing right here. So we need to figure out the 4th derivative by using product. So I have first times the derivative of the 2nd, gotta use chain, plus 2nd times the derivative of the 1st. Yeah, she looks kind of messy, I know, but we'll be fine, hopefully. Okay, so we are going to plug in 0 here and see what we get. Now, if we plug in 0, this thing just cancels out because this is 0 and this is 0, so that's just 0. So then the fourth derivative at 0 is going to be f prime of 0 times -2, aka only this part's right here. Okay, so f prime of 0 is 3. So we have the fourth derivative at 0 being -6. Okay, so that should give us hopefully enough information to give me the fourth degree Taylor polynomial. We know that f of 0 is 2. We know that my first derivative at 0 is 3. Now my second derivative is this lovely thing right here, and it tells us that it's just going to be negative f of x squared. If I were to plug in 0, this is just negative f of 0. Negative f of 0 is just going to be -2. So I have -2 x squared over 2 factorial. And then if I were to look at my third derivative, me plugging in 0, well, if I plug in 0 here, this is just going to be 0, so I'm going to ignore that term. And then the fourth derivative at 0 we found out was -6. So now we have -6 x to the fourth over 4 factorial. And that gives us my fourth degree Taylor polynomial for f about x is equal to 0. Okay, so for part B, we want to approximate f of 0.1. What's used to approximate f of 0.1. And we're given that the fifth derivative is less than or equal to 15. So that's going to be my maximum value there for 0 to 0.5. We want to use Lagrange error bound to show that this approximation is within 1 over 10 to the fifth of the exact value of f of 0.1. So basically we have my error, which is going to be this right here. That has to be less than my next derivative. In this case, we know that's going to be 15 here because I gave that to Mia. And then we are approximating 0.1. And since my center is at 0, this is just going to be 0.1 to the fifth over 5 factorial. Now, we can't just jump straight from here to here just because I want to show my intermediate subs to actually verify that. That's definitely going to be less than or equal to 1 over 10 to the fifth. So we are going to go ahead and simplify this a little bit and say that we have 15 over 5 factorial. And then we also have 0.1 to the fifth. I'm going to go ahead and put that down in the denominator and say 10 to the fifth. So I have that. And that right there, if I were to ignore the 15 and the 5 factorial, that's going to be less than or equal to 1 over 10 to the fifth. So there's your little justification there. Okay. Then part C, it says g is the function such that g of 0 is equal to 4. F prime of x is equal to e to the x times f of x. And we want to write the second degree Taylor polynomial for g about x is equal to 0. All right, so we already know what f of x is. And we kind of already know what e to the x is in terms of my Taylor polynomial. So for f of x, we know that's just going to be 2 plus 3x. I'm not going to do the other terms just because it's going to be too big because I only want the second degree Taylor polynomial there. And then we know that e to the x, if I were to build that, that's just going to be 1 plus x over 1 plus x squared over 2 factorial. In terms of that. So if I were to go ahead and build this or multiply this out, then I'm gonna have 2, 3x, 2x, let's see, 3x squared, x squared, and then this right here is going to be too big for us, which is what we don't want. Okay. All right, so that is going to give us a derivative of 2 plus 5x plus 4x squared. Then I realized that because we only want the second degree and because we are going to be integrating this, we kind of really don't need the 4x squared. So this right here is kind of useless. And this right here is kind of useless. Okay, so what we're going to do now is go ahead and integrate this right here. And that's going to give us our second degree Taylor polynomial. So integrating that gives us 2x plus 5 halves x squared plus c. Now, your c value here, okay, that should have been a g. Oopsies. Your c value here is going to be g of 0 is equal to 4, and then if I were to use that and solve that, that's going to be easy for us just because g of 0 is equal to 4, so c is 4. So that means that g of x is going to be 2x plus 5 halves x squared plus 4 in terms of my second degree Taylor polynomial for g about x is equal to 0. Lots of fun, I know. All right, I'm gonna skip 19. That should be self-explanatory, and then we'll do 20. So for 20, we have f being this lovely function right here, and we want to find the third degree Taylor polynomial for f about x is equal to 0. So unfortunately, I can't build this. Because I can't build this, we are going to use the definition of Taylor polynomials and take derivatives. I know. Quite sad. So f prime of x is going to be 2 cosine of 2x minus 2 sine of 2x. The second derivative is going to be negative 4 sine of 2x minus 4 cosine of 2x. And then the third derivative is going to be negative 8 sine of 2x plus 8. No, not sine. Oopsies. Cosine of 2x. And then 8 sine of 2x. Whew, okay. And then we are just plugging in 0 for my derivatives. Lucky for us, at sine of 0 is just going to give me 0, so I don't really care about sines. I only care about the cosines now. So if I were to do this, this is going to give me 1. This is going to give me negative 4. Well, just kidding, not 1, 2. This is going to give me 2. This is going to give me negative 4. And this is going to give me negative 8. And then also, if I were to plug in 0 in my original, that's just going to be 1. Okay, so building this, I am going to get, let's see, 1 plus 2x minus 4x squared over 2 factorial minus 8x cubed over 3 factorial. Okay, now part B says find the coefficient of x to the 19 in the Taylor series for f about x is equal to 0. Here's the thing. So if I were to take the fourth derivative here, okay, you'll realize that the fourth derivative here is going to be 16 sine of 2x plus 16 cosine of 2x, which gives me a fourth derivative of 16. Now, you're going to see that we are going to be alternating signs every two terms, because if you take the fifth derivative, you're going to get a 32. And then if you take the sixth derivative, you're going to get a negative 64 and so forth. In addition to that, you'll probably see that, hey, we're multiplying by 2 each time. So if I were to look at this in terms of making a general term, I might say that this is going to be in the form of 2 to the n over n factorial. And then we know that that's going to be x to the n. And we are alternating every two terms. So basically now I'm just going to plug in 19 into my lovely value of n to get 2 to the 19 over 19 factorial, and then we have x to the 19. Our next part is determining if, well, since it's talking about the coefficients, it's just going to be 2 over 19. 2 to the 19 over 19 factorial. And then our next part is determining if our coefficient is positive or negative, since we're alternating every two terms. Since we're alternating every two terms, and this is an odd, we have 1, 2, 3, 4. This is going to be 20, which means 19 is going to be this thing right here, which means that our coefficient is going to be negative. Okay. For part C, we know that the maximum derivative, the maximum fourth derivative has to be is 16 root 2. And we want to use Lagrange error bound to show that this lovely thing is less than 1 over 100. So we have my error here is less than or equal to my maximum derivative. In this case, they already gave it to me, 16 root 2. And then we're going to multiply by, in this case, 1/5. It's centered at 0, so we just have 1/5. And then the power is going to be 4 over 4 factorial. Now we just have to prove and justify that that is definitely less than 1 over 100. Just kidding, that should say 1 over 1,000. Oopsies. Okay, so we have 16 root 2. And then we have 5 to the 4th right here. We have 4 factorial right here. Now 4 factorial, remember, is 24. So we have that lovely thing right here. And then if I were to simplify 16 and 24, we get to 8, 12, 4, 6, 2/3. And then 5 to the 4th power is 625. And then if I do 3 times 625, I get 1870. That should be root 2. 1875. That is obviously going to be less than 1 over 1,000. Pretty fun, I know. All right, and then we have part D. We have g of x is equal to the integral from 0 to x f of t dt, and we want to write the third degree Taylor polynomial for g about x is equal to 0. Okay, so we already know that f of t is basically this, but with t. Okay, what was that? Like 4t. Now we are going to integrate this from 0 to x. So using our term by term integration, we are going to get t plus t squared minus 4t to the third over 3 times 2 factorial minus 8t to the fourth over 4 times 3 factorial plus c, but you'll realize that whenever we do that, it's gonna cancel out just because we're using ftc here from 0 to x. So then if I were to do that, I'm gonna get x plus x squared minus 4x to the third over 3 times 2 factorial minus 8x to the fourth over 4 times 3 factorial here. Well, plot twist. Since it's only asking us for the third degree Taylor polynomial, this will be wrong because I'm using x to the fourth right here. So technically, we didn't need this. We didn't need this. So it's only this part right here that we actually want in terms of my third degree Taylor polynomial. Now, do you want to simplify this? Sure, if you want to. If you don't want to, that's fine. But that's our answer there. Okay. Just see a lot of practice in terms of Lagrange and alternating series error. It's not that bad. You'll get maybe like 2 or 3 points in terms of doing Lagrange or alternating series error. So knowing how to do them will give you those easy points. You just need to do a lot of practice.